Thank you very much, Sean, for that excellent hydrogen one-on-one introduction across multiple sectors of technology. And now we'll be having our Q&A panel, and we'll get started with the audience questions that has been accumulating for a while now due to this previous instruction. And I guess the first question should be more direct to Zane's presentation, but it's open to all panelists regarding the transportation costs for hydrogen, comparing between pipeline, trucking, and shipping. Saying if you wouldn't mind taking a lead.
Absolutely, and it's a really astute question, and we found broadly through our scenario analysis that I know it's an unsatisfying answer, but it depends. The optimal transportation infrastructure for hydrogen largely depends on a few different factors. One of those factors being the volume of hydrogen that you need to move. And so thinking about that hydrogen in energy terms, as Sean was saying, hydrogen is gravimetrically very energy dense. So that would be energy per unit of mass, but energy per unit of volume, volumetric energy density of hydrogen is extremely low. So if you need to move a lot of hydrogen, if you have a high energy demand at your end use, then something like a gaseous tube truck is not going to be adequate. But if you need a very flexible hydrogen demand where you don't need a lot of hydrogen at your end point, then maybe gaseous tube trucking is your optimal solution. Now you can liquefy hydrogen and put it on a tube truck as well. That said, hydrogen has an extremely low liquefaction point. And so that means you have to get that hydrogen very, very, very cold before it will liquefy. And that's an energy intensive process. And anytime you use energy, you add to the cost. So you can achieve a greater volumetric energy density by introducing liquefaction, but in doing so, you add to the cost. You also add to the amount of infrastructure necessary because you need a hydrogen liquefaction facility at your origin, and you need a hydrogen gasification facility at your destination. The final land transportation option that we really look at today is the pipeline, and I think this is the end game for large scale hydrogen adoption across sectors. To achieve pipelines would enable the treatment of hydrogen as a true energy commodity, much in the same way that we move natural gas around today. It would really enable the true commodification of hydrogen in a way that the multi-access pipelines could unleash liquidity in the hydrogen markets and really allow for ubiquitous transportation of hydrogen from origin to destination. They're very costly. They require specialized steel compounds to keep the steel from embrittling. They require a really specialized infrastructure around the pipelines to avoid leakage of the hydrogen, and especially to avoid leakage of the hydrogen in a scenario where it might pool up wherever it's leaking and potentially lead to explosions. So there's challenges around that. And I believe Mark has actually done a lot of research on this. I believe, Mark, I've read some of your research on this topic, so maybe you have more to add on this. But the final answer for me is it really depends on what stage of development your hydrogen market is at.
Yeah, I don't think I have anything to add on that, Zane. I think that was a good summary. I think in terms of the basic economics, there's a shift as you get to higher volume and longer distances. I think that's what Zane has mentioned. So the liquefaction and pipeline are really more economic at larger scale, longer distances. And we see that today with the hydrogen pipelines in the Gulf Coast, where refineries are using very large volumes of hydrogen. So that makes pipeline delivery an economic option.
And Sean, and if you have anything to add regarding this topic?
No, great coverage, Zane.
Got it. Thank you very much. Deeply appreciate the great answer, Zane. And thank you, Mark, for adding to the answer. And I guess that will lead to a second point and broader question. Is the future of hydrogen centralized or distributed? Or does that depend on the actual application between your industrial application for high heat application, for heavy transportation application, for power application? For anyone who's chooses started wants to start.
I'll jump in with something with a brief point. In general, I think natural gas is a good comparison for a lot of things about hydrogen. like the way that we do it with natural gas is going to be very similar to the way that we do it with hydrogen. So if this hydrogen stuff comes to pass, then there are going to be a lot of pipelines that carry hydrogen, and that's going to be how a lot of the transportation happens, especially at large scale. So yeah, that's a kind of a starting point, but I think that my co-panelists will have a better detailed answer.
Yeah, I think I can add to that. The map I showed earlier of electrolysis units in the US, a lot of those are small enough where delivery by truck is actually more challenging or more expensive, and it might be for the particular application of hydrogen. So small electrolysis units are important. Thank you, that slide. Are important for particular applications. So semiconductors is one of those. I think another place where the economics work for distributed is, as was mentioned, isolated grids, smart grids that have sort of their own independent economics, local economics, and then also island communities, some military bases where just the economics of electricity supply are a lot different than the average large-scale grid.
I would add just one other thought to that. I think that was an excellent answer. One other thought that I would add is obviously the scale of production from these industrial fossil-based facilities is much larger and really highlights the centralized approach to hydrogen production. Although there are small-scale, more modular SMR units being produced today in kind of the startup sphere, but one interesting variable is the distribution of geologic storage capacity. Sean talked about geologic storage of hydrogen, and I talked about geologic storage of CO2. There's a lot of regions of the world that have ample access to the geologic structures that enable CO2 storage, that would enable very much so centralized large-scale blue hydrogen production. There's also regions of the world where you just don't have access to that CO2 storage, and so you can't have a domestic blue hydrogen supply chain. And so like Japan is one of these regions that doesn't really have much in the way of the geologic structures necessary to store CO2 at scale, and doesn't necessarily have the ample access to low-cost renewables that you would want to see very low-cost renewable hydrogen production. So in this case, you're going to be seeing more distributed production. You're going to see longer supply chains develop. In other situations, that it could be very different.
Thank you very much, everyone. And I guess after Ting Zhong's latest answer regarding renewable energy, is green hydrogen now in this prime time ready to go, where technology risk has been completely risked and now just a matter of scaling up? Put another way, is the challenge of green hydrogen a matter of economics and not a matter of technology now?
I'd say so, yes. If it were cheaper, I think we'd see it deployed at enormous scale tomorrow. There's no significant technology risk. I think that it's finance worthy.
Mark, Rosine, anything else you want to add? I think Zane probably has a better handle on some of the market activities globally, but I think in terms of low carbon energy in general, we expect countries, regions that have really strong climate change policies to really provide a lot of economic support for green hydrogen. One of the complications there is it depends upon the end use of the hydrogen. So if the hydrogen's being used to back up the grid, there are a lot of ways, low-cost ways to decarbonize the grid. So that's maybe not the strongest advantage. If it's being used to decarbonize transportation or industry, we know that it's more challenging economically to take the carbon out of those systems. So if there are policy mechanisms in place to support decarbonization of those difficult sectors, then we would expect green hydrogen to have a stronger economic advantage compared to other decarbonization options.
That was a really excellent answer, Mark. The one thing I would add from our perspective is in tracking the projects that have been announced in the renewable hydrogen space. We've seen that the vast majority of electrolysis projects today do have government support from the nation or state that they're being announced in. And so this shows that today, for a project to get a yes on their FID, there's almost always a government backing. And we think that that's going to be characteristic of the renewable hydrogen markets in particular, but low carbon hydrogen markets broadly for quite some time now. And that's not necessarily a bad thing. We've seen similar practices in getting solar at scale, where solar used to be extremely expensive until government and tax bases made the investment necessary to get it at scale and to get those prices down. We've seen the same thing happening with EVs, and now, lo and behold, EVs are accounting for 20% of auto sales in Germany and 20% of auto sales in France. So there's nothing wrong with that government investment, but for the near term, we definitely see that the economics require for yes on the FID, the economics almost ubiquitously require some government support.
Thank you, everyone. And Mark, one quick question specifically towards DOE. The Anali's member was asking if DOE is still funding research into materials development for hydrogen storage via absorption or other means, perhaps. And do we see a future in these kind of researches?
Yeah, so that's a good question. And if it's okay, Derek, I can send out a website with more details on that topic. But the quick answer is that DOE has supported a lot of different materials research on storage for many years. There's a really broad portfolio. Today we see high pressure gaseous storage and liquid storage being commercialized, but there are many other options at different phases of commercialization, R&D progress, and I can send out a link for more details on those R&D projects.
Thank you, Mark. And if you don't mind, you can just post a link in the chat, or if you can send a link to us and we can send it to an audience member afterwards.
Great.
Thank you. And now, I guess looking at more of a globally, I know transportation isn't as frequently mentioned. Maybe we can start with Sean, but does hydrogen fuel have a future in locomotive market globally speaking?
I don't know if the question is specifically about trains or transport, but I mean, either way, the answer depends on who you ask. But certainly there are a lot of pilot scale projects that within trains, usually because someone along the route objects to an electrification overhead wire. Yeah, the broader question I covered as well as I could, but in summary, especially for ships and planes, it's very hard to imagine how we're going to get away from molecular fuels, and hydrogen is one of the few ways. Hydrogen and hydrogen-based fuels are one of the few ways to decarbonize those applications.
Thank you very much, Sean. And I guess moving on to something looking towards the future for all panelists, what do you see as the biggest, the largest hydrogen market by 2040? Industrial application, transportation, or power?
I would say that largely speaking, we anticipate seeing hydrogen, low carbon hydrogen in particular, making a very big play in industry. The chemical sector and industrial heating are a really promising use case for low carbon hydrogen, where electrification is much less likely to make a play. If you look at transportation, particularly road transportation, battery electrification, I agree with what Sean said in his presentation, and it's kind of Platz's standard reference case as well, that we're sort of path dependent on electrification in road transportation. And increasingly, we're also seeing electrification, battery electrification in moving out of light duty vehicles into medium and heavy duty vehicles in short haul applications, in drayage trucks, in garbage trucks, in urban buses. And having very good economics to make that leap, and battery technology is improving. So transportation, especially road transportation, begins to look like a harder sell for hydrogen, with the exception of long haul heavy duty and the production of synthetic hydrocarbons such as sustainable aviation fuel or methanol for ship marine propulsion. But industry really has a lot of utilizations for hydrogen. I know we talked about steel earlier. The direct reduction of iron has not only a really promising use case for low carbon hydrogen, but provides significant bang for your buck on decarbonization per kilogram of hydrogen. We found that utilizing even your gray fossil hydrogen to displace metallurgical coal, coking coal, PCI coal in the steel production process can achieve significant decarbonization. You start to move that into low carbon hydrogen, and you can really see significant decarbonizations that could be triggered at relatively low carbon tax. And so we really are looking to industrial applications, both in the short term and in the long term, as being a significant call for low carbon hydrogen.
Thank you very much, Thane. Mark and Sean, anything to add?
No.
And I guess sort of branch off on that in terms of looking into the future. Is there any discussion about to put the safety concern for hydrogen storage in areas of possible high population density, if it's more likely than not the future is going to be distributed hydrogen instead of centralized hydrogen?
Yes, I think this is Mark. I tried to answer that earlier. I think really it depends upon the local economics for the energy system that's being considered. So we see a strong case for, say, island communities that want to be low carbon, military bases that have actually a mandate to be low carbon, these special economic niche markets, which are not necessarily small, they can be fairly large scale investments, but the economics are really sort of unique. That being said, we do have some hydrogen refueling stations that have distributed electrolysis production, but given the retail prices of electricity, that's challenging economically.
Absolutely. And Sean and Zane?
Not as far as hydrogen safety, not a significant concern for most of the manufacturers that we've talked to, most of the consumers that we've talked to. Broadly speaking, there's a lot of industry experience handling, moving, consuming, producing hydrogen. It's been produced at scale around the world for many decades. And so there's a lot of intelligence in this space. Now, we talk about ammonia a lot as a synthetic hydrogen carrier, anhydrous ammonia in particular. And there's also a lot of industry experience in handling ammonia, but ammonia has the potential to be very toxic, especially if we're talking about marine applications, and ammonia spills in the ocean ways high level of toxicity. And so there's concerns, no doubt. But the industry, from our experience and from the conversations that I've had, the industry's prepared.
Sean, anything to add?
I would say safety is there's a lot of work to be done on education and communication about the safety of hydrogen, but I would say the engineering side of making it safe is largely on track. And Zane had everything there is to say about ammonia as well.
Gosh, thank you all very much. And one last question as we wrap up Q&A from each of the panelists. What kind of policy do you envision will be the most effective in promoting hydrogen use, regardless of application, in the next few decades? Given the example, for example, feed-in tariff for solar, and now the ITC, as well as ITC for solar and PTC for wind.
I'll jump in with a couple of comments. There's basically anywhere where there's a carbon price of over $100 a ton is green hydrogen is already pretty viable right now. And there are a lot of little weird niche markets like that. In my regulatory area, I'm familiar with the LCFS in California and the renewable natural gas attribute in in other parts of the U.S. Have effective carbon prices above that. So in many cases, those kinds of regimes are already here. The other bullet I wanted to add on is that electricity costs themselves, when you look at wholesale costs, are already pretty compatible with producing commercially viable green hydrogen. But what the problem that you run into when you're trying to model these projects is transmission and delivery costs and kind of add-on charges above and beyond the cost of the electricity on the grid. And there are some emerging regimes, pricing regimes, where hydrogen production does not have to pay that. For instance, in the California ISO's NGR, non-generated resource program, and that is, I think, the number one thing that would make hydrogen commercially viable. But I don't know. There are a million things that you could add on. Certainly, feed-in tariffs and pipeline injection policies are another market that would drive a lot of volume.
I can just add a couple things to that. I think the point about carbon prices is really important. And I think for economy-wide carbon prices, you can get a lot of decarbonization for fairly low carbon prices. But some of the markets where hydrogen is going to have an advantage, you need a different carbon signal just for that particular sector. So the low carbon fuel standard that Sean just mentioned is an important example of that, where it's a particular carbon price mechanism just for the transportation sector. I think the other thing that's interesting is that electrolysis units, in addition to just the straight up economics, which we showed some examples of, they also provide grid services that are helpful for managing the overall grid. And so energy commissions, regulatory structures that can valorize, place a value on those services appropriately will help improve the economics of electrolysis.
I would add one other point that we've seen that we think is very interesting and something that we've been keeping an eye on, and that's gas grid blending quotas. If you look at a lot of the hydrogen strategies that have been announced, a lot of them play around with gas grid blending quotas for low or zero carbon hydrogen. And there's two interesting dynamics at play here. One, a blending quota, if the federal government, if Biden came out tomorrow and said 2% of all the gas in the grid by volume has to be zero carbon hydrogen in 2023, you can imagine investment would flood into low carbon hydrogen supply. And so this is a very useful tool to, at relatively no cost to the government, scale up investment in supply. On the other hand, by utilizing hydrogen to displace natural gas in the grid, you achieve very little in the way of decarbonization benefits versus utilization of that same kilogram of hydrogen to displace coal use in steel, or the kilowatt hour of renewable power that you use to produce that hydrogen to displace a coal-fired power plant. So it's a cost and benefit policy. It is not necessarily an optimal decarbonization pathway, but it is a useful policy to incentivize investment into low carbon hydrogen supply, and something that we're seeing in the playbook for a lot of nations, and something to keep an eye on over the next couple of years as a potential option, a potential policy lever that might get pulled.
Thank you all very much for that excellent question, and that will be the end of our Q&A panel. Thank you very much, Mark, Sean, and Zane for coming, and deeply appreciate your time.